So here I have reorganized the roadmap in a more linear way. So you can see here in the first column, this is our program for the first quarter. So that here will be Q1. And this here will be Q2. And now I will refer to this roadmap throughout the semester to make sure you roughly know where we are in the class. So for this first quarter, the first 2 weeks we'll start slowly. We'll look at scaling analysis. We'll do a number of examples of scaling analysis to start seeing also what kind of problems we'll see in fluid dynamics. We'll also discuss notations and do a few mathematical reminders before we'll move to the bigger part of this first quarter, which will be here deriving the governing equations of fluid mechanics, and that will mean discussing conservation, mass conservation, momentum equation. We'll derive them from the control volume level down to the differential level, and the boundary conditions. So this will take us roughly 3 to 4 weeks, and then we'll have 1 or 2 weeks left before the end of the quarter to start discussing the simpler flows where we can neglect viscosity, which are inviscid flows, and Bernoulli equations. So after that, you will have your midterm, and we'll move on to the second quarter. So as you can see, we will not discuss a particular technology or emphasize particular applications in fluid dynamics. Fluid dynamics is really relevant to a range of engineering problems, and so the class will be quite fundamental. And so I wanted to spend a few seconds just laying out what the goals were for the class. So the goals for IFD, the goals for IFD. And so the main goal, the first thing we'll do is to formulate the theoretical framework for fluid dynamics. So formulate the theoretical framework for fluid dynamics. And essentially, this means deriving Navier-Stokes equations from first principles. And so once we know what the equations of fluid mechanics are and we understand where they come from, we can look at, of course, different applications. And there, what we will do is introduce and derive what I will call the classic or the canonical problems and solutions of fluid dynamics. So introduce and derive the classical solutions in fluid dynamics. So, for example, that would be things that you've seen before: Poiseuille flow, flow around a cylinder, or a Couette flow. And of course, these problems are simplified problems. So when we'll derive them, you might think, well, this doesn't really look like anything I can see in any relevant application. But really, those problems are very important because they allow us to understand the flow physics. They allow us to understand what happens in the flow. So the goal there is to get insight into the physics of the flow. So to get insight into the flow physics. And once we've done that, so once we have the Navier-Stokes equation and we've derived really the key important classical solutions for different flow regimes, that should lay the foundation for more topical courses. So IFD as sort of the foundation on which you can build and take then later classes in compressible gas dynamics or in turbulence or in multi-phase flow. So the goal here is to have the tools at hand to then go on further and take more topical courses. So lay the foundation for topical courses. Compressible gas dynamics, turbulence, for example. Okay, and the last thing I want to do and discuss in this short section is the discussion what the general approach is in fluid dynamics. So what is, a little bit about the culture. How do you approach a problem in fluid dynamics? And the reason why I do this is because if you are later on interested in a career in fluid dynamics, that's definitely part of the steps that you will take. But this is also how a lot of the homework problems are structured, and how a lot of the exam problems are structured. And so fluid dynamics really any problem in fluid dynamics really start with experimental observations. So the first thing really are experiments. And there are a lot of very beautiful experiments in fluid dynamics. So it could be a very simple experiment, and here I'll take as an example that we will discuss at the very end of the class. And so let's say that we have the following situation. So this is just an example, but you could start with a simple problem where you have a stratified fluid. A stratified fluid is a fluid where you have different layers of different densities. So as soon as you have different layers of different densities, you call that a stratified fluid. So we have a simple stratification with two layers of fluid, a lighter fluid, so lower density at the bottom. So we have at the bottom a light fluid, and at the top we have a denser fluid. So that's a simple stratification. So what happens when we have that? So we can do an experiment, and the experiment would look a little bit like this. So here you have a simple glass of water, and the experimentalist here is going to create a stratification. So this blue layer here on top now is a layer of water mixed with a certain dye, and this layer here is denser than the layer on the bottom. Now there's a trick to that, because of course let me pause that. If you think about this simple example, this looks a lot like an inverted pendulum. Right? So if you have an inverted pendulum where you have a mass which is heavy on top like this, then you expect this to be unstable. So this is going to fall down. And so this is a very similar situation. This stratified fluid is unstable, as you will see in the video. And so to start up your experiment and not have the denser fluid immediately falling to the bottom, you have to use a trick. Right? And so the trick that the experimentalists here use is that this layer of fluid is initially heated, such that it is really lighter than this layer of fluid, and as it cools down, it will become heavier, and then the stratification will be unstable. So of course, when they first put this blue layer here, it is a stable stratification because the blue layer is slightly lighter, but as it cools down, it will become heavier, and then you'll see the instability develop in the form of these mushrooms. Right? So you observe in fluid dynamics, you will do this kind of experiment, and you observe something, and here you observe an instability. You can see that there is a certain length scale maybe associated with the emergence of this instability, but that would be a classical experimental observation in fluid dynamics. This is where you start. Okay, so what do we do with that? So we can summarize our experimental observations. Right, so we started with a denser fluid on top of a lighter fluid. And what we see is this instability. The lighter fluid is going to rise as the denser fluid, so the more heavy fluid is going to drop. That is called a Rayleigh-Taylor instability. So Rayleigh-Taylor instability. Now, on top of that, actually, which is not part of the problem we're discussing now, but if you carefully looked at these snapshots, so those are simulations and those are not experiments, but what you can see is something else, right? You see that the fluid, the lighter fluid now here is rising and the heavier fluid is dropping. And so what you have here is a shear flow, and what you see developing here, we've seen in the previous videos, are Kelvin-Helmholtz instability. Kelvin-Helmholtz instability. All right, so now we've made a number of experimental observations. We have our experiments, and the first thing that you would do is do a scaling analysis. And before you start doing the scaling analysis, what one would do is try to identify what are the relevant physical phenomena in this particular problem. So what are the important physical ingredients? And so I think at first this is the hardest part, because it requires some a certain familiarity with fluids, but this is also the most important one, the important part. Once you've correctly identified the dominant physical phenomena, then usually you are on a good track to solve the problem. So oftentimes it is complicated and yet easier than you think. So you have to identify what will be the important physical parameters in this problem. So if the container had a given size, for example, I don't know what the container is here, but then there would be a length scale. It could be a length scale. Something else which is clearly important is the stratification itself. So the density difference would be an important parameter. So the density of the light and the dense fluid. Now when you look at this, of course, at the core, what causes the instability? It's gravity, right? It's a gravity-driven instability, so gravity, the acceleration of gravity will also be an important parameter. Now what else could be important? Well, you have here a free interface. If this was oil and that was water, sorry, that would be the other way around if it was to be unstable. So if this was water and this was oil, then there will be an interfacial tension here, which might be relevant. So maybe the interfacial tension is important. Interfacial tension. And then, of course, and that is something which will be a constant discussion in this class. Is viscosity important, or is inertia important, or both? So, what is the importance of relative importance of viscosity, for viscous forces, and inertial forces? So once you've identified a number of these parameters, what you then do is a scaling analysis, and this we will discuss later. And in the scaling analysis, what you try to determine is what is the relative importance of all of these forces, and then essentially simplify the problem and only keep the physical phenomena which are really relevant to the system. So in some cases the interfacial tension might not be important, or in other cases it might be. That would depend on the fluids that we use. In some cases perhaps the viscous forces could be neglected, but in others, if in the experiment the fluid was very viscous, then viscous forces could not be neglected. So on the base of a scaling analysis, by using non-dimensional numbers, oftentimes one can simplify the problem and make the problem simpler to a degree where it can then be more easily modeled and solved. So the next step then is to model the system. So model the system, and that means once you've done the scaling analysis is to write the appropriate simplification of the Navier-Stokes equation. Of course, you could also always just write the Navier-Stokes equation, but usually what you want is to write the appropriate form of the governing equations, or the appropriate simplification of the Navier-Stokes equation. So write the appropriate simplification of the governing equation. Simplification of the governing equations. And this we'll discuss in all of the different situations. You know, in some cases it might be appropriate to just directly start from the boundary layer equations, for instance, or from the lubrication equations, or from the Euler's equation. But in order to get there and have those equations, one really needs to first do the scaling analysis. And if one has done the scaling analysis right and written the equations which are simple enough that we can solve them, then we can solve the equations. So resolution of the equation. And so that means in general, in fluid dynamics, at least in IFD, where we will only look at incompressible fluids, that means solving for the velocity field and the pressure field. Now sometimes I say velocity or pressure field, but sometimes what you're interested is neither the velocity field nor the pressure field, but it could be that you are interested in a quantity like the force or the drag or the lift, or you're interested in the time scale of an instability. Yeah? So you know, it could be finding the velocity field or the pressure field, but in some cases one would have to deduce from the velocity field, for instance, and the pressure field, a force or a lift. So find or compute a quantity of interest, such as a force or a time scale in the case of an instability. Now in IFD, this step of computing the solution will always, well, at least most of the time, it will look the motion of solving a particular equation would look similar to something that we will have done when we solved one of those classical canonical problems that I've discussed earlier on. And so once you've resolved the equations, oftentimes what you would do is, from the solution that you get, you verify the validity of the assumptions that you made, and also see if we can make new predictions. So that is yeah, the conclusion of a problem. You know, if you can predict some new experimental observation, then your whole model is very solid. So make new predictions that lead to new experiments.